This lecture is based on the textbook Combinatorics and Graph Theory, section 1.3.4, Counting Trees. In this section, we will discuss results on counting the number of spanning trees in a graph. First, we will look at the Cayley's tree formula. It gives us a way to count the number of different labeled trees on n vertices. We think of the vertices as being fixed, and then we consider all the ways to draw a tree on those fixed vertices. When there are 3 vertices, there are 3 ways to draw trees, and there are 16 ways to draw label trees on 4 vertices. So Cayley's tree formula was first proved by Cayley, but the proof technique we will describe here is a newer method. We will have a one-to-one correspondence between labeled trees and the set of all sequences of length n-2 whose entries come from the set 1 through n. And so it's easy to count such sequences from what we have learned. So what we will do is we multiply n because there are n choices from this set, and we multiply that n-2 times, and that is why there are n to the power of n-2 distinct labeled trees on n vertices. So first we look at the map from a tree to a sequence. Start with a tree and label the vertices 1 through n. The first step is to start at I equals 0. Let t naught be equal to t. In our example, this is our t. We will find the leaf on the first tree with the smallest label and call it v. So the smallest labeled leaf here is 2. So this would be our first v. We then record in this evolving sequence the label of v's neighbor. So we know that v only has one neighbor because v is a leaf. By definition, it only has one label. The neighbor of v here is 4, so we record 4, the neighbor of vertex 2. In the next step, we remove v from ti to create a new tree with a larger index. So here I remove the vertex 2 from the tree t naught to make a new tree called t1. In the next step, if my new tree is already the tree on 2 vertices with 1 edge, I stop. Otherwise, I increment I by 1 and I go back to step number 2. And because here T1 is not yet the tree on 2 vertices, I continue. I look at the leaf on T1 with the smallest label and call it V. So the leaf with smallest label is this leaf 4. In the next step, I record in my sequence the label of the neighbor of 4. The neighbor of 4 is 3, so I record 3 in the sequence, and then I remove V, so I remove 4 from T1 to create a new tree T2. So this is my T2, and I keep going. I go back to step number 2. I find the leaf on T2 with the smallest label and call it V. The leaf with smallest label is labeled 5. And I record the neighbor of vertex 5 in my sequence. So the neighbor is 1, so I add the number 1. And then I remove this leaf 5 to make a new tree, call it T3. And again, I look at the leaf with smallest label, so that's 6. The neighbor of 6 is 3, so I record 3 in my sequence. And I remove 6 from the tree to make T4. And in T4, the smallest labeled leaf is labeled 3. So I circle that. This is my current V. The neighbor of vertex 3 is vertex 1. So I record 1 in my sequence. And then I remove this leaf 3 to make a new tree called T5. But now I see that T5 is K2. So I stop. And my sequence for this given tree is 4, 3, 1, 3, 1. So let's look at some other smaller examples. When there are only 3 vertices, we know that there are only 3 labeled trees. So let's give the sequence for each of them. So for the first tree, the leaf with smallest label is A. In the second tree, the leaf with smallest label is also A. And in the third tree, the leaf with smallest label is B. So the neighbor of A is B, so I write down B here. The neighbor of A here is C, so I write down C. The neighbor of B is A, so I write down A. So I have labeled I have given the map from each tree to the sequence. So I can do the same for all of the labeled trees on 4 vertices. So in purple, I have circled the leaf with smallest label. And I look at, for example, in this tree, the neighbor of A is B, so I write down B. The neighbor of A is C, so I write down C. The neighbor of B is A, so I write down A. The neighbor of C is A, so I write down A. And then I go to the next step where I cut off these leaves. So now I'm looking at this subtree, and I have box in blue the leaf with smallest label. So here B is the smallest label, also B, A, and A. And now the neighbor of B is D, so I record D. The neighbor of B is D, so I record D. The neighbor of A is C, I record C. The neighbor of A is B, so I record B. And once I have removed the vertex that I have box, I get K2, so I stop. And so in this page I have also labeled each tree with its sequence, and you can check. Notice how all of the sequence here is distinct, and the sequence for the 4 trees at the bottom have constant sequence. So next, let's talk about the inverse map. So given a sequence, we want to assign a label tree. So I start with a sequence sigma of length k, and the entries can come from the set 1 through k plus 1. In our example, this is my sigma, so it's the same sequence that we got just now. And I draw k plus 2 vertices, label them 1 through k plus 2, and set S to be the set 1 through k plus 2. I start with I being 0, and I let sigma 0 be sigma, and I let S0 be the original S, and I let J be the smallest number in S0 that does not appear in the sequence sigma 0. So the smallest number in S0 that does not appear in sigma 0 is 2. So I set my J to be 2. And then I look at the vertex whose subscript appears first in the sequence sigma 0. So that would be 4. And so what I will do is place an edge between 4 and J, which is 2. So that's this edge. And in the next step, I remove the first number in the sequence sigma 0 to create a new sequence sigma 1. So here I remove 4. I remove A1 from sigma 0, and I get sigma 1 without the 4. And if the and I also remove J from the set Si to create a new set Si plus 1. So I remove J, which is 2, from S0 to give me new S1. And if this new sequence is empty, then I will place an edge and then stop, but otherwise I will increment I by 1 and then return to step 3. So now I will return to step 3. So now again I pick a new J, so this J has to be the smallest number in S1 that does not appear in the sequence sigma 1. So that number is 4. And then I connect this vertex 4 with the first entry of sigma 1, which is 3. So I connect 4 and 3. And then I remove the first number in the sequence sigma 1. So I remove 3 to get sigma 2. And I also remove j, which is 4, from S1 to get new S2. And I go back to step number 3, where now I have to pick a new j. So the j is again the smallest number in S2 that does not appear in the sequence sigma 2. This number is 5, so that's 5. I connect that with the first entry of sigma 2, so I connect 1 and 5. And I remove the first number in the sequence of sigma 2 to get sigma 3. And I remove j, which is 5, from S2 to get S3. And I keep going. I look at I go to step 3. Let j be the smallest number in S3 that does not appear in the sequence sigma 3. So that number is 6. So I connect the number 6 with the vertex 3. So I get this edge. And now I remove the first entry of sigma 3 to get just 1. And now I remove 6 to get us 4. So I have 1, 3, 7. It's still, my sequence is not empty yet, so I keep going. I look at the smallest entry in S4 that does not appear in sigma 4, so that's 3. So I connect 3 with 1. I get this edge. And the next step is I remove the first entry in sigma 4, so I get this empty sequence. And I remove j from S4 to get 1 and 7. So now I will place an edge between these two vertices in S5. So I connect 7 and 1. And I stop, and I have a tree. And I get exactly the same tree that we looked at before. So convince yourself that these two are really the same tree. And so that is the explanation for the Cayley's tree theorem. Now let's talk about another result called matrix tree theorem. So Cayley's theorem gives us a count on the number of spanning trees of complete labeled graphs, basically. So matrix tree theorem gives us a way to count the number of spanning trees of labeled graphs in general. So first we need some definition. We already learned about the adjacency matrix from before. And now another definition is, given a graph, we can compute the degree matrix of the graph. And basically it's a diagonal matrix where the diagonal entries are the vertex degrees, so here, and then all of the other entries are 0. And another definition is from linear algebra. Given an n by n matrix, the ij cofactor is defined to be -1 to the power of I plus j times the determinant of the same matrix, but you remove the ith row and the jth column. So basically you will get an n minus 1 times n minus 1 matrix, but you remove all of the entries in row I and all of the entries in column j. So now we're ready to state the matrix tree theorem. Given a connected labeled graph G with adjacency matrix A and degree matrix D, the number of unique spanning trees of this graph G is equal to the value of any cofactor of the matrix D minus A. So it doesn't matter what you choose for I and J, the number would be the same. So let's look at an example. Here we have a labeled graph G, and there are exactly 8 spanning trees. So let's check that using the matrix tree theorem, we actually get 8. So first compute the degree matrix D of G. So because vertex 1 and vertex 2 is of degree 2, we have this entry 2 and 2. Vertex 3 and 4 each has degree 3, so we have entry 3 and 3. And the adjacency matrix, so it will be 0 along the diagonal. Here is seeing what happened between 1 and 2. There is no edge between 1 and 2, so we have 0, but there is an edge 1, 3, and there is an edge 1, 4, and that's why you have these entries 1. And now we will take D minus A, so it's a pointwise subtraction, so 2 minus 0 is 2, 0 minus 0 is 0, 0 minus 1 is negative 1, and so on. And it doesn't matter which cofactor you use, so I might as well choose the 1, 1 cofactor of D minus A. So remember that to get the 1, 1 cofactor, I basically cross out the I row, so I cross out the first row and I cross out the first column, and I'm left with this matrix. And because negative 1 to the power of 1 plus 1 is 1, I just have to compute the determinant of this 3 by 3 matrix, and we can check that we in fact got the number 8. Okay, so let's look at just some of the exercises. So it's possible to show that in the proof sequence of a tree, each vertex will appear in a sequence exactly the degree of the vertex minus 1. So for example, in this tree here, the vertex 1 has degree 5, so the number 1 should appear 5 times, or not 5 times, but 5 minus 1 times, so it should appear 4 times. And all of the other vertices are leaves, so they should not appear at all. So the proof sequence should be 1, 1, 1, 1. And if we look at a path graph, the leaf 1 and 4 should not appear at all, but 2 has degree 2, so 2 should appear once, and 3 should appear once also. So this information should help you figure out how to compute, how to answer question 4 and question 5.